All right, so we're still talking about the common emitter amplifier high frequency response. And you just draw the circuit here really quickly. Yes, we're continuing what we talked about on Monday. Or it's a continuation in as much as it's the same topic, but we're going to approach it in a couple of different ways now because the feedback capacitance tends to make, actually, hold on. Erase that, sorry. That's a low frequency capacitor, so it shouldn't be here. Here's our sig, the in. RC in parallel with RL. So we had a capacitance C mu between our base and collector. C pi between our base and our emitter. When I drew it the other day, I drew the terminal of C pi connected directly at ground. But because our emitter is at ground, it's the same thing. I'm just drawing it slightly differently today for literally no reason whatsoever. And then we also had this capacitance CCS, and we took our output voltage here, right? So this is a circuit that we analyzed directly on Monday, I feel like today is Wednesday. And it was doable, but it was a bit annoying. And the thing that made it the most annoying, actually, whether or not you realize this, is this capacitor right here, C mu. What made it annoying in particular was the fact that it connected our output node effectively to what we were considering to be our input node, which was the Thevenin representation of that input stage. So what we're going to talk about first today is what's called Miller's theorem, and it is a method for effectively allowing us to refer some portion of that feedback capacitance to the input side of the amplifier stage and some portion to the output side of the amplifier stage, which will give us something that looks like a more traditional common emitter amplifier that we can analyze more easily. Okay. So let's talk about Miller's theorem. So let's say that we have a two-port network. Okay. So I'm going to call this node X. I'm going to call this node over here Y, such that we have some voltage here Vx, and we have a voltage here Vy. That is simply K times the voltage Vx. So effectively, we have two ports, and we know that the voltage at the second port depends on the voltage at the first port by some factor. This might be representative of an amplifier or something, where the voltage at the output is simply the gain times the voltage at the input. Well, if we connect these two networks, so let's tie these guys together and put ground in the middle. And let's connect these two networks by a floating impedance that I'm going to call Z. So this floating impedance could represent a resistance, a capacitance, an inductance. In the context of our circuit, this Z is effectively playing the role of the capacitance C mu, right? So it's what's connecting the node X where we had our Thevenin voltage to the node Y where we took our output. So there's some amount of current flowing through that floating impedance Z if Vx and Vy are not equal. Okay. So Miller's theorem states that we can replace the network effectively like we have here on the left with one where here's X we put some impedance, I'm going to call it Zx, over here on the input side. I'm going to have my referred impedance Zy over here on the output side. So here's Y. Here's Vy is still should be K Vx. And what we're going to do to sort out what those impedances should be is we are going to enforce a couple of constraints here. Okay. And so our first constraint is that the current that's flowing through impedance Zx literally has to be the same current that was flowing through our original impedance Z. And on this side, we're going to say that the current that's flowing up through Zy, which I'm going to call Iy, must also be equal to that current I. So these two networks would be electrically equivalent because we see the same voltages at each set of terminals and the same amount of current is passing through the network. So any power transfer and all that kind of stuff, any power applied at the input, the exact same amount of power shows up at the output, regardless of which network we're looking at, right? Just basic electrical equivalence. Okay. So let's look at this current Ix. Okay. So Ix, to me, looking at our right-hand circuit, simply looks like the voltage Vx divided by the impedance Zx, right? Nothing more than Ohm's law there, nothing wild or crazy. We know this needs to be equal to the current I shown in our left-hand circuit. Well, what's the current I in our left-hand circuit? To me, that looks like Vx minus Vy over that floating impedance Z. And Vy is simply K times Vx. So I'm just going to substitute that in directly. And so I could say that this looks like Vx times 1 minus K divided by Z. So I have this relationship and this relationship that have to be equal to each other. Okay? So what I'm going to do is I'm simply just going to put those two things equal to each other and rearrange and solve for whatever Zx has to be in terms of our original impedance, Z. And in doing so, what we'll find is that the impedance Zx is just going to be Z divided by 1 minus K, our gain, as it were. We're going to do something similar for finding what the impedance ZY needs to be. So looking at my right-hand circuit or network, ZY looks like I2, IY, goodness gracious. What happens when I use a different notation? Anyway, this should be negative VY over ZY because we want the current flowing up through the device, right? Or negative K VX over ZY, which once again, this must equal I, and we know that we can express I from the left-hand circuit as Vx times 1 minus K divided by Z. So rearranging this expression, let me actually, so I'm saying this bit right here has to equal this bit right here, and then rearranging, and we find that ZY is Z over 1 minus 1 over the gain. So let's take this notion and apply it to our capacitance C mu. So we'll figure out how much is going to be referred to the X side of our circuit and how much is going to be referred to the Y side of our circuit. So first, let's start by understanding what our gain is here. So our gain is just going to be effectively the midband gain of our network because that's what relates Vx and Vy when this capacitance wasn't there, right? So our midband gain is us treating that capacitor effectively as if it were an open circuit because we're not at a high enough frequency for it to have any impact. So our midband gain is just K. Which for us is going to be negative GM R naught in parallel with RC. Our original impedance, Z, is just 1 over S C mu, right? And so putting these things together, what we should find is that Zx is going to be our original Z over 1 minus K. So that's going to look like 1 over S C mu times 1 minus K, where 1 minus K is 1 plus GM R naught in parallel with RC. Which we could call 1 over SCX, where CX in this case is simply C mu multiplied by a factor of 1 plus GM R naught in parallel with RC. So effectively, we see that the capacitance at the input side of things is going to get boosted by a very significant amount, right? So whatever the gain of our amplifier is in magnitude, C mu gets multiplied effectively by that gain plus 1 when it gets referred to the input side of things. If we look at ZY, we're going to have Z over 1 minus 1 over K. So that's going to be 1 over SC mu times 1 plus 1 over GM R naught in parallel with RC. Or 1 over SCY, where CY is just C mu times that factor of GM R naught in parallel with RC over 1 plus GM R naught in parallel with RC. All I did to get to here was express this guy as GM R naught in parallel with RC over GM R naught in parallel with RC. Actually, it might be supposed to be the one on top. Sorry. Yeah, it should be the one on top. Let me put it up here. My apologies for that algebraic mistake, but it's all going to be effectively the same thing because 1 plus the magnitude of our gain divided by the magnitude of our gain, as long as our gain is large, is effectively just 1. So CY is effectively just going to be C mu. So let's see what shakes out when we analyze the small signal model with these Miller capacitances in place, right? So our small signal model should look something like this. So here's our Thevenin voltage from before. Here's that resistance R sig prime. Here's our impedance 1 over S C pi. Here's our new impedance 1 over S CX. Sorry, that shouldn't be GM R naught, that should be GM VBE. My apologies. Here's our voltage VBE. Here's our resistance R naught prime from before. Here's our capacitance, excuse me, this should be 1 over S CS. And if here's node Y, we put in our 1 over SCY right here. Here's V out. This guy is grounded. I would argue that this is going to be way, way easier to analyze. John, did you have a question? Okay. So we can see pretty easily that these two capacitors are in parallel and these two capacitors are in parallel. So let's call this combination CX prime and this combination CY prime, for lack of a better thing. So from this, I would say that our output voltage is just going to be negative GM VBE times the impedance connected between node Y and ground, which would just be R naught in parallel, or excuse me, R naught prime in parallel with 1 over S CY prime. Anybody got beef with that? Just Ohm's law. What's VBE? Just use voltage division, right? So that would be VThev times 1 over SCX divided by R sig prime plus 1 over SCX. Prime, thank you. Yes, those are primed. Multiplying by SCX prime over SCX prime, this winds up looking like VThev times 1 over 1 plus S R sig prime CX prime. And from here, we could substitute in for VBE. So we'd have V out is equal to negative GM VThev times 1 over 1 plus S R sig prime CX prime times R naught in parallel with 1 over S, that's going to be R naught prime in parallel with 1 over S CY prime. And our voltage gain, so this would just be the ratio of V out to V thev negative GM R naught prime in parallel with 1 over S CY prime times 1 over 1 plus S R sig prime CX prime. And now we just need to sort out how to extract our mid-band gain from that thing. So are we all okay with this thus far? Anybody got any questions, comments, or concerns about my algebra here? So let's look at just this part that I underlined in red here. And the reason why I'm only messing with the part that I underlined in red is because I believe that the right hand of this is already in a really great form for me to figure out what pole is going to be contributed from that. And there's not going to be a zero, quite obviously, because the numerator is 1. So the right-hand side of this thing is already in a great form for us. So now we have to play around with the left-hand side of it, right? So we've got negative GM R naught prime in parallel with 1 over SCY prime. So whenever I have, let me do this over here in blue. So I have R in parallel with a capacitance. That's just R over SC divided by R plus 1 over SC, which is R divided by 1 plus SRC. My algebra there is correct, right? We saw this when we were looking at the low frequency response, and we calculated effectively ZE using this exact representation. So for us, this is going to look like negative GM times R naught prime divided by 1 plus S R naught prime times CY prime. What was R naught prime? So if I remember correctly, it was R naught in parallel with RC in parallel with RL. So when I substitute that in, I get negative GM. So I've got an R naught in parallel with an RC. That quantity in parallel with RL divided by 1 plus S R naught prime CY prime.
Just for the top or not running at the bottom.
See, because I'm trying to pull out an R naught in parallel with RC from the numerator for my midband gain. So right now I'm just kind of playing around with things to see how stuff shakes out. I might wind up doing it from the bottom, but I probably won't. So that is going to look like negative GM times R naught in parallel with RC times RL divided by 1 plus S R naught prime CY prime times R naught in parallel with RC plus RL. Are we okay with that? So from here, I would have negative GM R naught in parallel with RC times RL over R naught in parallel with RC plus RL plus S R naught in parallel with RC plus RL times R naught prime times CY prime. And I believe that is of a form that I can pull a pole from very easily. Right? So omega Z, let's call it 2, since this is the second expression we're looking at, is going to be negative R naught in parallel with RC plus RL divided by R naught in parallel with RC plus RL times R naught prime times whatever CY prime is. And up here, from this guy, we can see that our other pole, so let's call it omega P1, is just negative 1 over R sig prime dx prime. And that's our frequency response, right? So we've identified both of our poles from this particular way of looking at things. We don't get any zero information whatsoever because we don't have that feedback that's kind of forcing it to be there. So this is another just approximation technique effectively. If the analysis or the direct analysis poses to be just too damn difficult because we happen to have some sort of feedback impedance connecting our input node to our output node, the Miller method gives us a way around that. And it'll be relatively accurate. Yes, ma'am. It should, yes, because it's definitely a pole and not a zero. Thank you for that. All right, so here was our second method of kind of direct analysis style. Okay. So now I want to introduce to you guys the method of open circuit time constants. We did short circuit time constants for low frequency, right? Yeah. All right. So So the open circuit time constant method is just the high frequency version of the short circuit time constant method that we use to approximate where the location of our low frequency cutoff is. So the open circuit time constant method allows us to approximate where our high frequency cutoff is going to be. So we can use the open circuit time constant method to get one result, the short circuit time constant method to get the other result, and then we have some idea of what our amplifier's bandwidth will be, or the, the length of the midband region. So ultimately, we'll see that omega high will be approximately equal to 1 over the sum from I is equal to 1 to n of C sub I times R sub I, where C sub I is just we go through each individual capacitor in our system, and R sub I is the resistance seen by each of those individual capacitors, where all other capacitors are replaced by an open circuit. So let's start with the capacitance C pi. So what resistance does C pi see? Okay. So I've turned off my input signal, okay, because we're looking for a Thevenin equivalent resistance here. So this is R sig. Here's R1 in parallel with R2. Now I'm at my base terminal. Here's R pi. I'm using this open circuited set of terminals here to be where the capacitance C pi was. So these are the terminals that we're effectively looking into. But I'm going to keep on trucking over here. So let's see, this would be VBE. GMVBE. And then over here we have R naught. And then here we have RC in parallel with RL. So my C mu capacitance connected between my base and collector is being treated like an open circuit. My CCS capacitance connected between my collector and ground is being treated like an open circuit. And then we removed C pi and we're looking in through its open circuited terminals. So what do we see?
Is it R1 parallel?
So I think R sig is in parallel with all of those others because it's between the base node and ground. So it's just R thev. Right? So R C pi is R sig in parallel with R1, in parallel with R2, in parallel with R pi. Pretty straightforward there, right? What resistance does C mu see? So let's look at what we've got here. Here's our R sig. R1 in parallel with R2. Here's our base node. Here's R pi. Or not. And RC in parallel with RL. And then we're looking in through this set of terminals where C mu used to be. So I would argue that it's going to see the resistance to the left in series with the resistance to the right. Everybody okay with that? So what's the resistance to the left? RC pi. What's the resistance to the right?
R0.
R naught in parallel with RC in parallel with RL. So RC mu is just R sig in parallel with R1, in parallel with R2, in parallel with R pi, plus R naught in parallel with RC, in parallel with RL. And then lastly, what resistance does CCS see? So draw things out. Sig R1 in parallel with R2. So looking in through the terminals of CCS with C pi and C mu open circuited, what do we see? Yep, absolutely. So just to simplify some things here, right? If I am not mistaken, this is literally what we called R sig prime from earlier. And this is literally what we called R naught prime from earlier, which means this guy in the middle is just R sig prime plus R naught prime. Expressing it in that way, because it'll make it wildly easy to use this method for MOSFET-based amplifiers as well in that form. If we can figure out what R sig prime is for MOSFET-based amplifier, which will actually just be whatever that is when R pi goes to infinity, or just R sig in parallel with R1 in parallel with R2. R naught prime should be literally the exact same thing, except that we would replace RC with RD because we would have a drain resistance, not a collector resistance, right? Okay, so that is all of the different things that we can throw at a common emitter amplifier. For a common source amplifier, we could use literally the exact same relationships, replacing, so let's see, let's write this out here. So for a MOSFET, everywhere we see R pi, we replace it with an open circuit, right? Everywhere we see RC, we replace it with RD. Everywhere we saw RE, and so this is including for our low frequency analysis, we would replace it with RS. Everywhere we see C pi, we will replace it with CGS. Everywhere we see C mu, we would replace it with CGD. Everywhere we saw CCS, we would replace it with CDB. So the MOSFET has that fourth capacitor, right, between the source and the body. That's a high frequency capacitance between the source and the body. But for our common emitter amplifier at high frequencies, the source and the body is shorted out. So the source node is connected directly to ground. So that CSB capacitance is effectively shorted on both sides, so it shouldn't show up anywhere. Yes.
For the open circuit ramp up, I would like to drain like the short circuit ramp submitted, we get that like a one denominator.
Yes. Exact same. So we need one pole to be dominant. Otherwise, we're gonna have interactions and we need to use a different method. Yeah. And it's literally the exact same constraint. Yeah. So for what it's worth, when I ask you to solve problems or anything related to this, which hopefully I'll get a homework assignment and all that kind of jazz put up in the next day or two or before the end of the weekend. I will be very explicit about what method that I'm expecting you to use to do things. So it'll be questions like, where are our poles located with direct analysis? Where are our poles located with, use the open circuit time constant method and the short circuit time constant method to estimate the bandwidth of this amplifier kind of thing. I will be very deliberate in what I'm expecting you to use so that you know what to do, because I hit you with so many different ways to look at these damn things. So anyway. All right. So let's look at common base amplifier and let's just get started on this. Definitely will not have time to finish. So as a refresher, our fully biased common base amplifier is going to look something like this. So here we have some resistance R1. Here we have some resistance R2. And then we're going to include a bypass capacitor here, CB, that will prevent that base resistance R1 in parallel with R2 from influencing our midband gain, right? Because that base resistance tends to make the midband gain smaller. So we put the capacitor there to make sure that doesn't happen at low frequencies. Or at midband frequencies, sorry. Then over here, we have our emitter resistance RE. Here's CN. Here's R sig. Here's our input voltage. Up here we have VCC again. Here's RC. Here's C out. And I'm going to draw this a little odd. So I'm putting a ground thing up top here to place my resistor RL, just so that it's out of the way. And then here's our output. So we're going to approach this very similarly to how we approached the common emitter amplifier. We're going to break things up into discrete stages, right? So I'm going to consider everything under this dashed line to be my input stage. And I'm going to call the voltage at the emitter node Vx. Everything to the right of this oddly shaped dashed line is going to be my output stage, and then everything else is my amplifier stage. So my amplifier stage is going to contribute a transfer function of Vy over Vx. My output stage is going to contribute a transfer function of V out over Vy. And my input stage is going to contribute a transfer function of Vx over Vn, exactly like we did for our common emitter amplifier. Yes.
And Vy is at the
Yep, so VY is at the collector node exactly like it was before. Thank you for that. All right, so starting with our low frequency analysis. Let's look at the amplifier stage. So I'm going to draw a small signal representation here. I have some base impedance. So this is just everything that's connected between my base node and AC ground. Here's R pi and VBE. I'm going to effectively apply a voltage Vx directly at my emitter node. So it's serving as the input voltage for this stage. Here I have GM VBE in parallel with R naught. Here's my collector node. Here's the output of this stage, which is the voltage VY. And then here I have some impedance ZC. So let's define some things here really quickly. ZB is nothing more than R1 in parallel with R2 in parallel with 1 over SCB. So we could express that as R1 in parallel with R2 over 1 plus S R1 in parallel with R2 times CB. So are we all okay with that representation of ZB? So let's start. Are we all okay with me saying it's the impedance of resistor R1 in parallel with R2 in parallel with the impedance of that capacitor? I don't know how you couldn't see that. I just wanted to make sure we're all on the same page. What's ZC going to look like? Literally the exact same thing that we saw in our common emitter amplifier. RC in parallel with the series combination of that output capacitor and RL, right? So RC in parallel with RL plus 1 over SC out. And using literally the results from when we saw this earlier, we're going to have RC times 1 plus S RL C out divided by 1 plus S times RC plus RL times C out. So if you look back through your 335 notes, you should see this exact circuit, except that ZB would be replaced by a resistance RB and ZC was replaced by a resistance RC. This is nothing more than a common base amplifier with an included base resistance. So using the results of 335 and just replacing every RB with ZB and every RC with ZC, we would have a voltage gain relationship of Vy over Vx is equal to R pi plus GM R pi R naught plus ZB times R naught in parallel with ZC divided by R naught times R pi plus ZB. So as you can imagine from looking at this thing, this would be incredibly gross to analyze in the frequency domain because we've got impedances in the numerator, parallel combinations of impedances, all of that kind of good stuff. So we are going to make a similar approximation to what we did with our common emitter amplifier. And this actually is probably already in your notes from when we covered the common base amplifier in 335. So in 335, we found that this big ugly thing was approximately equal to GM R pi times R naught in parallel with, I'm just going to substitute in here ZC, divided by R pi plus ZB. And I'm going to go ahead and pull out that R naught in parallel with ZC so that we have GM R naught in parallel with ZC times the ratio of R pi over R pi plus ZB. So I've broken up the amplifier stage just like I did with the common emitter amplifier into something that it's fairly obvious. This is where I'm going to pull my mid-band gain out of, and it's going to probably contribute a pole of 0. And I've got this other thing right here that has an impedance, so it's going to have some frequency dependent characteristics as well. So let's look at the R pi over R pi plus ZB bit first, just like we did with our common emitter amplifier. So R pi over R pi plus ZB is R pi over R pi plus R1 in parallel with R2 over 1 plus S R1 in parallel with R2 times CB. So now I'm going to multiply through by 1 plus S R1 in parallel with R2 CB over 1 plus S R1 in parallel with R2 times CB. And so that gives me R pi times 1 plus S R1 in parallel with R2 CB divided by R1 in parallel with R2 plus R pi times 1 plus S R1 in parallel with R2 CB, which could be written as R pi plus S R pi R1 in parallel with R2 CB over R pi plus R1 in parallel with R2 plus S R pi times R1 in parallel with R2 CB. And therefore, our first 0 for the amplifier stage is at R pi negative R pi divided by R pi R1 in parallel with R2 CB. And quite obviously, those guys just cancel each other out. Our pole is going to be at negative R pi plus R1 in parallel with R2 divided by R pi times R1 in parallel with R2 CB. You all okay with this? Did I mess up any of the moving stuff around to find my poles and zeros? I don't think I did, but I wouldn't put it past me. Okay. So now let's look at the GM R naught in parallel with ZC bit, which, by the way, is literally identical to the negative GM R naught in parallel with ZC bit that we had from our common emitter amplifier, except that we no longer have the negative sign. So I'm not going to do literally any of the algebra again. I'm just going to write stuff down because we've already seen it before. So GM R naught in parallel with ZC winds up looking like GM times R naught in parallel with RC times 1 plus S RL C out divided by 1 plus S times R naught RC plus RL plus RC times RL, all divided by R naught plus RC times C out. Again, that bit was derived when we were looking at the common emitter amplifier. So our second zero from the amplifier stage is just -1 over RL C out. And our second pole from our amplifier stage is -1 over R naught times RC plus RL plus RC times RL, all over R naught plus RC, all times C out. So we know how the amplifier portion of this thing works. Looking at the output stage, we effectively have this circuit. So here's our voltage Vy between our node Y and ground. We have a resistance RC, and then our other path, we have 1 over SC out in series with RL, and our output voltage is the voltage drop across that resistance RL. Literally the exact same thing as we, yes.
That on that plus or the RC or
I'm 80% sure it's supposed to be an RC. Looking at my terrible handwriting, let's put it as RC. It should be literally letter for letter, the exact same thing as what we saw with the common emitter amplifier. I just didn't happen to bring those notes with me today. So if you go back in those notes and you find where we were manipulating negative GM R naught in parallel with ZC, it's literally just that, except that we threw away the negative sign because there isn't a negative sign for the common base amplifier. Okay, but I'm more than 50% sure that's supposed to be an RC. All this means is that I really have to get off my ass and just make these into PowerPoints. I hate it so much. All right. So we've seen this part before as well. So V out over VY is going to look like SRL C out divided by 1 plus SRL C out. And therefore, omega Z out is 0 and omega P out is -1 over RL C out. All right, we're going to stop here. The input stage analysis is going to look extremely similar to effectively what we reduced our input stage analysis down to for the common emitter amplifier, but I did not have time to do all of the gross algebra. So I'll take care of that, and then we'll knock out the input stage in a tight 10 minutes at the beginning of Friday's class. Yes. I have not.
Do the answers.
It's on my to-do list. So I need to get it done specifically. Like, I know that you guys are dreading it. It's not going to be that bad. But it is something that we use for both ABET accreditation and SACS accreditation. So I kind of have to make you guys do it. So I'll get it up soon.